So this question is based on the crystal field theory. In crystal field theory, we have learnt about the splitting of d subshell. As we know that the d subshell have got 5 orbitals. They are dxy, dyz, dzx, dx square minus y square, and dz square. As you can see that I have used two different colors. It is just because of the fact that dx square minus y square and dz square, they are directional set of orbitals because they have their lobes directed along the axis, while the rest of the three dx, y, yz and zx, they have their lobes in the diagonal positions and not directed along the axis. So they are called the non-directional set of orbitals. Now when a particular metal is subjected to a particular situation where the ligands approach from different directions, then according to the direction in which the ligands approach, these 5 orbitals, they get split into two sets, the non-directional set and the directional set, in 3:2 ratio. This question is based on an octahedral geometry. How would you know that? See over here, there are 2 ammonia ligands and 4 water ligands. Now you know that both ammonia and water, they are monodentate ligands. So we can say that this complex is a complex which has the central metal ion, that is the copper ion, ligated by 6 ligands. That means its coordination number is 6. For coordination number 6, we have the octahedral geometry. In case of the octahedral geometry, the ligands, they approach right along the axis. Let these be the axis, then these would be the direction in which the ligands would approach each other. Now basically when this kind of situation occurs, then the directional set of orbitals, as they have their lobes directed along the axis, they are in the firing line. They interact more with the ligands and hence they get more destabilized. Okay, so let's draw the CFT diagram after the D splitting. So before splitting, all the 5 orbitals, d orbitals, they have the same energy. But after splitting, that means when the ligands have approached, the splitting occurs in case of an octahedral geometry in this fashion, where the non-directional set of orbitals, they are below the barycenter, since they are somewhat stabilized, as their lobes are not directly in the direction along which the ligands are approaching. While for the directional set of orbitals, their lobes, as they are directed right along the axis, they will be destabilized, right, in case of an octahedral geometry. This is called the EG set of orbitals and these are the T2G set of orbitals. Next, we have to find out the oxidation state of copper in this particular complex. For copper, let us consider X to be the oxidation state. It is ligated by 2 ammonia molecules, that means 2 ammonia ligands which are neutral, and 4 water ligands, they are also neutral, and the overall charge is +2. So if you solve this equation, X is also equal to +2. So copper is in its +2 oxidation state over here, whose electron configuration is argon 4s0 3d9. The 4s electrons and 1 electron from the d subshell have gone out because it has lost 2 electrons. Now let us fill up these electrons over here. 1 2 3 4 5, you have to accommodate for 9, right? 3d9. So this is the 3d subshell. 6 6 7 8 9. Now over here also similarly, now in case of transition metals, there is a particular phenomenon of electron transition called the DD transition. As you can see, this is the DD transitions. Okay, this is also a D subshell and this is also a D subshell, because after splitting the D subshells, they are differentiated into 2 sets, right? So now any electron from the lower D set of orbitals may be transited to the higher ones. Now there is only option over here for this one because it is unpaired one. The one which is right over here won't have any transition possible for it because it is already a paired one. Okay, so now if any of these 2 electrons have to be transited to the upper orbitals, then it will be the one with the lower spin. Okay, similarly for this one, the one with the lower spin or downward spin will be possible for the transition, and similarly from here also. So that leaves us with 3 possibilities, one from here, one from here, and the third one from here. So these are the 3 DD transitions that are possible over here. 3 DD transitions, because for transition of electrons, the spin must be absolutely anti-parallel. So this will be the correct answer, number C. Well, let's now talk about free radical chain reactions. Free radical chain reactions are very fast, and an example for a free radical chain reaction is a polymerization, free radical polymerization reaction. Okay, now free radical chain reaction or free radical reactions occur in 3 steps. Number 1, the initiation, propagation, and number 3 is termination. Propagation steps may be more than one. Let us take some examples to make ourselves understand what these 3 types of steps mean. Say for example, we have a molecule, mostly a mostly a non-polar molecule, which is susceptible to undergo a homolytic cleavage, right? So let us have this diatomic homonuclear molecule A2. If this molecule gets somewhat split in this fashion, that these 2 shared pair of electrons, they are equally shared, then we would have 2 free radicals. Okay, similar types of 2 free radicals. This is a step which marks the initiation of a particular reaction, hence it is called the initiation step. Now why would I say that this would mark as the initiation of a reaction? Because these free radicals are quite reactive, and hence they would, it's like just falling a pack of cards. If you just push one, the others will be followed very soon. So one such free radical rather, would hit another such molecule, and this process will go on. So let me show you over here. So this is a propagation step. What do you mean by propagation? The literal meaning of propagation is to go on, right? And what would be a termination step like? Say if you have a free radical and say you have a propagating chain like this, it may also be a single free radical also, and if they combine to just stop this reaction, then it will be called as a termination. Okay, I hope it is somewhat clear now. Now the question over here asks that which of the following steps, step 1, 2, 3, or rather the question is asking what is the nature of step 2 and step 3. That means over here and over here. See, let me first elaborately write down step 2 and step 3. Okay, so step 2 first. Here there is a bromine free radical. This reacts to a hydrogen molecule. This is what we would expect, and then HBr and H dot will be formed, right? So what among these three options, which would be resembling this one? See, it is resembling this one, isn't it so? Yes, so it is a propagation type step. Let's see the other option, that means the other step, step number 3. Here, step number 3, here we have a hydrogen free radical. Okay, and that free radical is reacting to a bromine molecule. Okay, so now this is what we are getting over here. So once again, it is a propagation step. So both step 2 and step 3 represent a chain propagation. Okay, let's now look into the options. Chain propagating, chain terminating, option A is wrong. Branching and terminating, wrong. Chain propagating, chain propagating. So option C is correct.